In this chapter, we study differential equations. In many natural phenomena, quantities grow or decay at a rate that's proportional to their size. For example, if n of t is the number of individuals in a population at time t, then we might expect the rate of change of n to be proportional to n. In other words, the rate of change, the derivative of n with respect to time, we might expect to be proportional to n, where this constant r here is the constant of proportionality. Why is this a reasonable expectation? Well, you can imagine, on average, each individual in the population is reproducing at some rate. And so if we doubled the population size, for example, then the total rate of change of the population ought to double as well. In other words, if each individual is reproducing at some per capita rate r, then the rate of change of the total population size ought to be equal to r times the number of individuals in the population. So this constant of proportionality r here in this model is usually referred to as the per capita growth rate. The per individual growth rate is another way to think of that. Now this equation, n prime equals r times n, is called a differential equation. And the definition of a differential equation is given here. A differential equation is simply an equation involving the derivative of an unknown function and possibly the function itself as well. So for example, in this instance, the unknown function is n, and this equation involves the derivative of n on the left-hand side, n prime, as well as the function itself, n of t, on the right-hand side. Now, in addition to having a differential equation for something like the rate of growth of a population, we might also know the initial population size. And together these form what's called an initial value problem. An initial value problem is simply a problem that involves a differential equation for some unknown function, like the function here, n prime equals Rn, as well as an initial value for this function. In this case, n at t equals 0 is equal to 100. And the problem, the initial value problem, is to find the unknown function n that satisfies both of these conditions. The function n that satisfies both the differential equation, n prime equals Rn, as well as the initial condition, n at time 0 equals 100. Now we've already seen some examples of differential equations previously, and here's one from physics. This is an example of a moving object where s of t is a function giving the position of the object at time t. Now, as an example, let's suppose that the velocity of the object at any time is given by 2t plus 1. And of course, the velocity is just the derivative of the position function, and so we can write this as a differential equation. S prime of t is equal to 2t plus 1. Now, let's suppose also that we know the initial position of the object is s at time 0 equals 1. Together, these give an initial value problem for the position of the object, and the problem is to find the function s of t that satisfies both of these conditions. Well, we've already solved this kind of differential equation previously. What we've done is simply anti-differentiate the differential equation. So, for example, if we anti-differentiate this equation here, we get s at time t is equal to t squared plus t plus some constant of integration c. That's the general solution for this differential equation by simply anti-differentiating it. And in order to solve this initial value problem, we need to choose this constant of integration c so that this function also satisfies the initial condition. And we can do that quite easily, as we've done before. At time 0, this equation tells us that we have s of 0 equals 0 squared plus 0 plus c, and that's just equal to c. But we also know that at s of time 0, the position has to be 1. S of time 0 equals 1. Together, these therefore mean that c has to equal 1. And this means that the solution to the initial value problem is s of t is equal to t squared plus t plus 1. That's the solution to the initial value problem. It satisfies both the differential equation and the initial value. And we can verify that it's a solution to the initial value problem by plugging it into both of these equations. In terms of the differential equation, if we differentiate our putative solution, we get s prime is equal to 2t plus 1. And we can see that that does indeed satisfy the differential equation. That's exactly as it's meant to be. And we can also check that it satisfies the initial condition by plugging in a value of t equals 0, in which case we get 0 squared plus 0 plus 1, which equals 1. So this verifies that this is indeed the solution to this initial value problem. Now, although we've seen other differential equations like this before, there's an important difference between this differential equation and the differential equation for population growth that we introduced at the beginning of this video. In this physics example, you can see that on the right-hand side of the differential equation, there's a function that involves only t. And so in order to solve that differential equation, all we had to do was anti-differentiate it. On the other hand, for our model of population growth, you can see that on the right-hand side of the equation, there is no explicit dependence on t. Instead, the derivative n prime of t is equal to some constant times n itself. And so we can't anti-differentiate the right-hand side to get the solution because we don't know what n of t is. As a result, we're going to have to learn other techniques for solving this kind of differential equation. And more generally, we might have a differential equation that kind of mixes both of these two scenarios. For example, we might have a differential equation for y, where y prime is equal to some function of t, 2t plus 1, times the function y itself. And again, we're going to need to learn other techniques in order to solve this kind of differential equation. Well, we can make a bit of progress before we learn any techniques, though, just by guessing. This differential equation tells us that whatever this unknown function n is, it has to be such that when we differentiate it, we get the function back times some constant r. And we've already seen functions that have this property. Exponential functions have the property that when you differentiate them, you get the exponential function back, possibly multiplied by some constant. So, for example, if we choose the function n of t is equal to some constant c e to the rt as our exponential function, we can verify that this does indeed satisfy the differential equation. If I differentiate this equation, I get n prime of t is equal to, and then differentiating the exponential, I'm going to have an r times c e to the rt. And how can we verify that that does indeed satisfy the differential equation? Because this equation looks quite different from our original differential equation. As a general way to verify whether or not you have a solution to a differential equation, what you want to do is compute the derivative and then substitute the derivative and the function itself into the differential equation. What I mean by that is I want to take what we've just computed for n prime and write that down for the left-hand side of the differential equation here. So I'll have r c e to the rt. And then I want to check whether or not that equals what I get on the right-hand side if I take r and I multiply it to n. Well, n is defined here to be c e to the rt, so that's r times c e to the rt. And we can see that these two sides do indeed equal one another, and so this is indeed a solution to the differential equation. In fact, it's a family of solutions because the constant c is not defined yet. We can also now choose this constant c so that our initial condition is satisfied. Using this as our solution and plugging in t equals 0, we get n of 0 is equal to c e to the r times 0, which is just equal to c. And we also know from our initial condition that n of 0 has to equal 100. So together, these conditions tell us that c must equal 100. And as a result, that gives us the solution to our initial value problem. N of t is equal to 100 e to the rt. That is the solution to this initial value problem. If we were to plug this into the differential equation, we can see that for this particular choice of c, it does again satisfy the differential equation as it did above. And we can also see that it satisfies the initial condition, because when I plug a value of t equals 0 in here, I simply get n of 0 equals 100. So here's a simple example where we have a model, a differential equation for a model of population growth. It's an example where we don't yet know any techniques for solving this differential equation, but we were able to guess the solution. What we're going to do in this chapter is learn a variety of techniques for analyzing, studying, and solving differential equations.